Okay, in this video we're going to be talking about slightly different motion than what we've been talking about in the past. We're also going to talk about vector addition, which we've done in previous videos, but we're going to take a look at it in a slightly different way than we have in the past, in a little bit more detail. So let's start with this. In the past we've talked about objects that are traveling at a constant velocity. And if an object's traveling at a constant velocity, then that means if you check on where it is over equal periods of time, it will have traveled equal distances in the same direction each time. So this car on this slide is traveling at a constant velocity, even though we have it labeled V0, V1, V2, V3. We know that each of those velocities is actually the exact same because the vector arrows are the same size and because it is traveling the same distance from T0 to T1 to T2 to T3. We've also talked about objects with constant accelerations, which means they are constantly changing their velocity. So each velocity it then has a delta V added to it before you see the next velocity. So that newer velocity is now bigger and it has a delta V added to it also. Since the velocity keeps getting bigger by adding delta V over and over and over to it, that means that the car is traveling greater distances in each successive time period. Let's take a look at that vector addition in a little bit more detail. If V initial plus delta V equals V final, then visually what that would look like is we draw our V initial vector and delta V is drawn from the end of the V initial vector. And so our V final has to start where the V initial vector started and end where the delta V vector ended. That's how we get the bigger vector for V final than we did for V initial. Remember this slide from, I think, video 6? The point with this was that the acceleration and the velocity do not have to be in the same direction. The acceleration does have to be in the same direction as delta V. Mathematically, acceleration gets its direction from the delta V vector. And by Newton's second law, the acceleration vector will be in the exact same direction as the force vector. So force, acceleration, and delta V all will be in the same direction. But that does not have to be in the same direction as velocity. If it is in the same direction as velocity, that car is speeding up. If it's in the opposite direction of velocity, that car is slowing down. And so we've also talked about an object that is slowing. It has this initial velocity, and you add a delta V to it that is pointed the opposite direction of the velocity vector. And so by the next time that you look at the vehicle, the velocity vector is smaller, and then you again add a delta V in the opposite direction. So it gets progressively smaller and smaller velocity vectors as you go, meaning it's traveling smaller and smaller distances each period of time. The way that vector addition works is visually it works by the exact same rules. You start with a V initial and then you add your delta V so that you start drawing your delta V vector at the end of your V initial vector. Your V final vector still has to start where V initial started and end where delta V ended. That's how visually you draw vectors when you're adding vectors together. Our new topic is how to deal with the kinematics for an object that is moving at constant speed but is changing direction. Since the velocity vector for an object includes direction, if an object is traveling at constant speed but it is changing direction, it means it's experiencing a delta V, which would mean that it's experiencing an acceleration, and you might not have expected that. And then by Newton's second law, that would mean it's also experiencing a non-zero net force. How exactly this works is what we're getting into in this video right here. Visually, it's going to go by the exact same rules. We're going to start out with our V initial, and I need to add a delta V on somewhere. But I don't want it to cause my V initial to turn into a V final that's a different size. My V initial and V final have to be the same size vector if the object is traveling at constant speed. So delta V, how is it supposed to be added on at all? Well, my V final is not in the same direction as my V initial. My V final at each successive time period will be in a different direction. So my delta V, instead of being added on like the one that we just had disappear on our slide here, it will be added on like this. As the time periods get smaller and smaller and smaller, the delta V will get smaller and smaller and smaller, and it will approach a limit as time approaches zero. But it will continue to be, even as time approaches zero, it will continue to be that visually V initial plus delta V does give you a V final vector, where that vector starts where V initial starts and ends where delta V ends. As time gets smaller and smaller and smaller, and the delta V gets smaller and smaller and smaller, you would find that the angle between V initial and delta V approaches 90 degrees. For an object traveling in a circle, delta V and velocity at any given moment are perpendicular to each other. And delta V is the same direction as acceleration. Delta V is the exact same direction as the net force. That means that all of those vectors, the net force, the acceleration, and the delta V, are perpendicular to the velocity for an object that is traveling in a circle. Thus, the net force at any given moment is directed toward the center of the circle. If delta V is not perfectly perpendicular with the velocity vector, then that means some component of the delta V vector is going to be perpendicular to velocity, but some component of it is not going to be. And so in a situation like this one, you would have a delta V perpendicular that's causing the car to change direction, but you would also have a delta V parallel to the initial velocity. That would be causing this car to speed up as it changes direction. That's possible. We're not going to deal with objects that do both at the same time. It's also possible, of course, to have a delta V vector that is not perpendicular to the initial velocity, but it includes a perpendicular component and a component parallel to the initial velocity, but actually in the exact opposite direction. That would be an example of a car that is turning to its left, but also slowing down. We will be dealing with objects that are traveling in perfect circles in this chapter, and objects that are traveling in perfect circles have a delta V that is perfectly perpendicular to the velocity at any given moment. For example, obviously in that video, the ball was experiencing some slowing as it went on, but assume a more perfect scenario. We saw it traveling in a circle. Assume for a moment that it didn't slow as it went. Whether it slowed or not, what direction would you expect to see the force on the ball as it traveled around the circle? It has to be that the edge of the pan is providing a contact force, a normal force on the ball. And that force has to be pointed to the middle of the pan if the ball actually is traveling at a constant speed. That contact force, of course, the ball pushes back on the pan, but on a free body diagram of the ball, you would expect to see the gravitational force pointed straight down and the normal force of the bottom of the pan pointed straight up, plus this green vector that I showed was the side of the pan pushing on the ball. One of the big tricks with dealing with objects that are traveling in circular motion is to figure out that your free body diagram actually needs to be viewed from the side. If we were to draw the gravity vector on here, it would not be pointing to the bottom of this page, the bottom of this photograph. Gravity is pulling the ball straight toward the center of the earth, and this image was taken with a camera that's looking straight down, so the vector would be pointed directly away from the camera, and the normal force from the bottom of the pan would be pointed directly at the camera. And that's not a good way to try to draw that. So you want to imagine that you are down at the level of the ball, looking at it from the side. The gravitational force pulls down, the normal force pushes up. They add up to 0 in the y direction, or I guess the z direction from the perspective of the camera. And as you're looking straight down at that normal vector, you don't need to worry about the ball accelerating toward you or away from you, what looks like up or down on this free body diagram. What you do have to worry about is that the normal force is drawn as that green force normal. Now, drawing it to the right versus drawing it to the left on this free body diagram actually doesn't really matter, because what you want to do is you want to recognize that that normal force is pointed toward the center of the circle. The free body diagram does not change as you move around the circle if you recognize that you have drawn that green force to represent the contact between the ball and the pan, specifically the pan pushing on the ball, and of course we know that the ball is pushing back on the pan by Newton's third law. This green force that I've drawn on here is always pointed toward the center of the circle, so it is sometimes called a radial force or a centripetal force. Not centrifugal, centripetal with a P, not an F. If you want to know the difference between them, we'll talk a little bit about it, but also your textbook does a pretty good job explaining it. The term centripetal force or radial force should not ever appear on your free body diagram. So to see how we're going to use that, you'll want to check the example video that follows this one. I do want to share with you this GIF from this guy that I follow on Twitter. He put together this image to try to emphasize that the force that would be required to make this object travel in a circle really does have to be a series of perpendicular contacts with the ball. And when we say a series of perpendicular contacts, of course we mean as the limit between contacts approaches 0. So approximately a consistent, constant perpendicular force touching the ball to make it travel in a circle. This is an example of a free body diagram for an object traveling in circular motion. You have the gravitational force pointed down, you have the normal force pointed up, and you have a frictional force that is causing this car to change its direction without speeding up or slowing down. If this car is turning left, then we know what kind of circle it's making is that we're standing on the edge of it, and the center of that circle is to our left, and so therefore the force is pointed to the left. But what is that force? You can say it's centripetal, but centripetal means pointed to the middle. So that would be a lot like if you drew a vector force pointed down, and I said, what is that? And you said, it's the down force. It's not the down force, it's the Earth's gravitational pull. It is downward, but down is not a good description of what it is. It's a good description of which direction it points. In this case, friction is what makes the car turn, friction between the tires and the road. If you don't have friction, then that's what causes cars to slide off the road in icy or muddy conditions. So if you're having trouble identifying what force it is that's making your object travel in a circle, you should be able to look at the situation and get a good sense of what that force is based on the description. And even if you're not sure what force it is, then you could leave some sort of description, it's a force between the tires and the road. But don't call it centripetal, because that is a direction description, not a type of force description. This slide is here to emphasize that it's important for you to be outside of the object that is traveling in a circle in order for you to have a good sense of what's happening, what force is causing the turn. If you're driving in a straight line and then you turn the wheel very suddenly to the right, you feel yourself pushed to the left. So they're describing that here as a fictitious force. It's not a force, it's that your body, inertia, is trying to travel in a straight line, and suddenly the car got turned to the right underneath you. This is less obvious in a car. It's more obvious in a situation like if you have left your coffee on the roof of your car and you're driving down the street. You're not in the vehicle, but rather on the roof of the vehicle. If you suddenly turn right, you would see that that coffee cup, if it struggles to stay with the vehicle at all, would continue going straight down the path of the street that the car had initially been traveling. I'm not encouraging you to try that as a experiment, but you might happen to see something like that someday, and then remember what's going on there. How this has to relate to the previous video where we were talking about rotation, not revolution, but rotation, where an object has this omega, this rotational or angular velocity, is that we don't mostly want to talk a lot about angular velocity. A little bit, but not a lot. What we do want to talk about is if you have a situation like this one, like this merry-go-round, then this merry-go-round or carousel is undergoing a rotation, but the child on the merry-go-round or carousel is not. The child is undergoing circular motion. They're undergoing they're experiencing a motion where they are traveling in a full circle, not where they are spinning on an axis. So when we are studying an object that is traveling in a circle, we want to talk about centripetal forces, and we're going to use some equations that I'm about to introduce for you here at the end of this video. An object that's traveling in a circular motion will be traveling at constant speed. It is possible to have an object that travels in a circular motion and speeds up or slows down. That is not at all what we are addressing in an introductory physics course. If it's traveling at constant speed, you want to be able to identify that that means it makes a lap of its circular motion every specific amount of time. We identified that specific amount of time in a previous video as the period, capital T. So the speed of the object at any given moment is the circumference of its circular path divided by the period of time it takes to travel that path. And that'll come out in meters per second if you're using your radius in meters. The velocity of your object at any given moment, its velocity, not its delta v, will be tangent to the path. And then delta v will be pointed toward the middle of the circular path. The equation for the acceleration of an object traveling in circular motion, we won't be using delta v over delta t anymore. What we'll be using is v squared over r, where v in this equation is your tangential velocity, your constant speed. If any of that seems confusing, I promise the example videos will clarify that. And Newton's second law still applies. So once you know the acceleration for an object that's traveling around a circle, its force, its net force acting on it, that we will call a centripetal force, whether it's tension or friction or normal force or whatever it is, the net force is going to equal ma. It's just that a is found with a different equation here than it was when we were traveling in straight lines or as projectiles. Any force that we've talked about can be a centripetal force. If you tie a rock to a string and spin it around like this, then the string tension is your centripetal force. In the frying pan video, it was the normal force between the frying pan side and the ball. And then, of course, the friction was described with the automobile. That's it for this video. Example problems on the way.